Hello students, welcome to EPG Pathshala. I am Vidya Kothekar. I had been Professor of Biophysics at All India Institute of Medical Sciences, Delhi, Professor of Bioinformatics at JP Institute of Information Technology, and Director and Professor of Bioinformatics at Dr. D.Y. Patil Biotechnology and Bioinformatics Institute, Pune. Today, I am going to discuss about a module, conformational properties of polypeptides and Ramachandran plot under the paper Biomolecules and their interactions. Amino acid sequence, that is the primary structure of protein, controls the folding, that is the secondary structure of polypeptide chain, into different secondary structural motifs based on the energetics of the interactions of the backbone and side chain with each other and formation of hydrogen bonds among the backbone carboxylic and amino groups. Latter pack against each other and gives rise to a tertiary structure of protein. And these tertiary structural subunits, they pack against each other to make quaternary structure and ultimately lead to a biological assembly, which is the business end of a protein. It is necessary for us to understand the conformational properties of polypeptides in order to understand the rules governing protein folding and its function. G N Ramachandran, one of the greatest Indian biophysicists, did a very pioneering work in this area. You know, the first protein structure of myoglobin was discovered in the year 1960 by a group of Kendrew et al. But just within 3 years, G N Ramachandran in India laid the basic foundation for understanding the conformational properties of polypeptides. Students, let's first see what are we going to learn in this module. First of all, I want to describe nomenclature, rotational angles in a peptide fragment. This is essential for further understanding of torsional angles. Next, I want to describe empirical potential energy function because it is used for computation of potential energy and then calculation of conformational maps. Thirdly, generation of a polypeptide. This is necessary. We start from some geometry and then we create various geometries of peptides using standard bond lengths, bond angle and dihedral angle data. Then I would like to describe methodology for computation of the conformational maps for polypeptide, and most important, I want to elaborate on what is Ramachandran plot. Nomenclature and rotational angles in a peptide fragment. We show in this picture a dipeptide fragment N C alpha C N C alpha C. The two peptide units are shown in red and blue color. Structural details such as bond lengths, bond angles and torsional angles are shown here. For example, C alpha C bond length is 1.52 angstrom. Cn bond length is 1.33 angstrom. Nc alpha bond length 1.45 angstrom. The bond angles around C atom are C alpha CO 121 degrees, OCN 123 degrees, C alpha CN 116 degrees, and these three groups make it a planar configuration. The torsional angles or dihedral angles around Nc alpha and C alpha C are defined as phi and psi. These are shown by yellow-green arrow for both peptide 1 and peptide 2, and these are suffixed by 1 and 2. Rotational flexibility around Nc alpha and C alpha C bonds. In rigid geometry method, the bond lengths, bond angles shown in the previous slide are considered to be fixed. Geometry around the peptide linkage is also rigid because of the partial double bonded nature of Hn and CO bonds. There is a flexibility for rotation around Nc alpha and C alpha C bonds. Dihedral angle IUPAC-IUB nomenclature. Consider a 4-atom sequence A, B, C and D. Now look from B to C and consider atom A at 12 o'clock position. The deviation of AB and CD bonds from each other is measured by the deviation of atom D from A. A clockwise rotation corresponds a positive value. How do you define a torsional or a dihedral angle? First, both these terms, torsional and dihedral, are used interchangeably. The torsional angle beta j is defined as the angle between the images of bonds jj dash and j2j3 dash. The clockwise rotation of the bond, which is the near bond jj dash, about the bond j dash j2 dash, to bring it, that is jj dash, in the direction of the distant bond j2 dash j3 dash, is taken as positive direction. Consider two wheels attached to the near bond and further bond, and a handle in the direction of the bond, near bond, attached to the near wheel. Now, let's rotate the near wheel till that handle or the bond comes in the direction of the further bond and measure the angle. In the present case, the angle is 300 degrees. So we know the difference between 300 and 60 degrees. Backbone torsional angles. The torsional angle phi is defined as rotation around N C alpha bond. We take 4-atom sequence starting from the previous residue Cn-1, then N of the residue C alpha and Cn, and the rotation Nc alpha is defined as phi. Rotational angle psi is defined as rotation about C alpha C bond. It is the angle amongst N C alpha N, Cn, and N of the next residue, N plus 1 residue, and the rotation is around C alpha N, Cn, and is called psi. Rotational angle omega is the rotation around the Cn bond. The 4-atom sequence for this is C alpha N, Cn, N plus 1, that is the next residue, and C alpha N plus 1, that is the next residue. But this angle is usually fixed around 180 degrees in all trans amino acids, and generally in all proteins. Most of the time we have only trans amino acids. 0 degrees in case of cis amino acids, and there are few exceptions. Cis-trans isomerization in proline and some unsubstituted amino acids as sarcosine are able to be populated both in cis and trans isomers. The transition between the two is a slow process which impedes protein folding. Backbone and side chain torsional angles. We show here a peptide backbone for I-1 to ith to I plus 1 unit. We show rotational angle phi around Nc alpha and C alpha C psi. Side chain torsional angles. For each side chain dihedral angle, the coordinates of 4 atoms are required. The table in the next slide contains the list of atoms and rotational angles. The angle chi1 is not calculated for alanine and glycine. Angle chi2 is not calculated for alanine, cysteine, glycine, serine, threonine, and valine. Angle chi3 is calculated for arginine, glutamine, glutamic acid, lysine, and methionine. Angle chi4 is calculated only for arginine and lysine, and angle chi5 is calculated for arginine only. The 4-atom sequence for these angles is shown in the next slide. The backbone torsional angle phi is defined as Cn-1 N C alpha C. We have omitted suffix N for the central amino acid. Angle psi for the backbone is defined as N C alpha C and N of the next residue. Angle omega is defined as C alpha of the previous residue N-1 C N C alpha. Chi1, which is the side chain rotational angle, is defined as N C alpha C beta C gamma. It defines the rotation around C alpha C beta bond. Chi2 is rotation around C beta C gamma bond and is defined as C alpha, C beta, C gamma and C delta. It is calculated for all amino acids except alanine, cysteine, glycine, serine, threonine and valine. Angle chi3 is most varied in different amino acids. In lysine, it is defined as C beta, C gamma, C delta, C epsilon. Methionine is defined as C beta, C gamma, S delta, C epsilon. Arginine, it is C beta, C gamma, C delta, N epsilon. And GLN and GLU, it is C beta, C gamma, C delta and O epsilon. Angle chi4 is also defined differently in arginine and lysine. In arginine, it is C gamma, C delta, N epsilon, C zeta, and lysine, it is C gamma, C delta, C epsilon, N zeta. Angle chi5 is seen only in the case of arginine. C delta, N epsilon, C zeta, and N eta. What is empirical potential energy function for conformational study of polypeptides? Conformation of a polypeptide can be studied using variety of theoretical methods, starting from ab initio quantum mechanical studies, semi-empirical, empirical quantum chemical methods, to purely empirical atom-atom based additive non-bonded potential. It is totally a parametric potential which is used for conformation energy calculation. Empirical potential energy function, we generally do not consider interaction about the first neighbors, that is the bonded interaction, interaction between the second neighbor, that is the three atoms which make the angle, and we are fully justified in neglecting these all bonded interaction and angle interaction and restrict ourselves only to non-bonded interactions, since our objective here is to study conformational degrees of freedom of a polypeptide and the energies of different conformations here, they differ by few kilocal per mole, and the bonded interactions can be neglected in that range. Empirical potential energy functions have gone through great improvement in several decades. Then people have incorporated different statistical methods as genetic algorithm, Monte Carlo method, etc. These have really expanded the scope of conformational analysis methods. That is, now we do not have to restrict only to two rotational angles, but we can have half a dozen or more number of rotations taken care of by. These methods are very important because they can deliver satisfactory results in a very reasonable period of time. What is a hard sphere potential? The origin of all empirical potential energy function can be traced back to the most celebrated work of Professor G N Ramachandran in 1963. He plotted sterically allowed regions for rotations around NC alpha phi and C alpha C psi bonds, taking account of only the dimensions of the atoms through van der Waals contact distances. He plotted these regions on two-dimensional plots phi versus psi. Conventionally, these are known as Ramachandran's phi psi maps or plots using van der Waals contact criteria. He used two different criteria. One was the normal criteria, and in the second, some adjustments were done and where the distances were allowed to reduce a little bit. And this criteria itself is equivalent to the Hart sphere potential. Hart sphere potential. It means that if R is greater than R0 between the two atoms, the approach of the two atoms is allowed. If R, distance between two atoms, is less than a particular value R0, then the approach of the two atoms is not allowed, as the potential energy becomes very large. We show in this picture, in this table, the contact criteria used by G N Ramachandran. He used two different values, ordinary criteria, and after making some adjustment for the allowed distances, a minimum contact criteria. For example, for CC bond, ordinarily it is 3.0 angstrom, whereas minimum 2.9 angstrom. CO bond, it is 2.8 angstrom and minimum is 2.7 angstrom. For ON, ordinary is 2.7 angstrom and minimum 2.6 angstrom. General form of empirical potential energy function is given below. The potential consists of four terms: non-bonded, U non, electrostatic, U electrostatic, H bonding, U H bond, and torsional, U tor. It is sum of all these four terms taken over all the pairs of non-bonded atoms, which means these are not connected by bond, so they cannot be first neighbor. These are not connected by angles, so they cannot be second neighbor. So they have to be separated by more than 3 bonds. So we see the mathematical expression for these 4 potential energy functions. U non is Lennard-Jones 612 potential given as A upon R12, which is a repulsive term, minus B upon R6, where A and B are the constants depending upon the type of atom, and R, the distance between a non-bonded pair of atoms. U electrostatic is given as 332 multiplied by Qi Qj divided by epsilon r, where Qi and Qj are the charges on the two atoms Ij, and r is the distance between these two non-bonded atoms. UH bond, or the hydrogen bonding contribution, is calculated for only H-bonded atom pairs. It is a 10-12 term and given as C upon R12 minus D upon R10, where C and D are the constants depending on the hydrogen bond donors and acceptors, and R the distance between the hydrogen bond donors and acceptors. The torsional term is a 4-atom term rather. It depends on the torsional angle around the central two atoms. It is described by a constant which is a barrier to the rotation k phi multiplied by 1 minus cos n times phi minus delta, where n is the foldedness of the potential and delta is the phase factor. The rotation around a single bond, for example H3C and CH3, does not have staggered or eclipsed conformation. This is the origin of the term torsional potential. Study of thermodynamic properties of ethanes and other molecules indicate that these rotations are not free but have barriers. For example, in case of ethane, the threefold torsional potential is shown in this picture, and it is represented by the same equation, half k phi, where k phi is the barrier to the rotation and phi is the dihedral angle. U tor increases when hydrogen atoms are replaced by bulkier atoms, and in this case the summation is taken over all the flexible angles. Like if we rotate only 2 bonds, then the summation will be of 2 terms. If there are 3 simultaneous rotations, the summation will be of 3 bonds. Thus, torsional potential U tor is a 4-atom term based on dihedral angle about an axis defined by the middle pair of atoms. For this term, the energy constant may be negative, indicating a maximum at cis conformation, and there may be several contributions with different periodicities for a given set of 4 atoms. Generation of a polypeptide geometries for different values of phi and psi. Starting geometry. The first requirement for calculation of the conformation energy is you should have starting geometry. This can be done using variety of methods. Most of the modeling programs like MOE, HyperChem, etc. give you sketchers. One can draw the molecule using these sketchers and get the initial or the starting coordinates. Cartesian coordinates determined by X-ray crystallography, NMR and other. If these are available already, then this can be used as a starting geometry. Internal to Cartesian coordinate conversion using Thomson's algorithm or any other algorithm. Here we start with the bond lengths, bond angle, torsional angle, and use a transformation to generate the Cartesian algorithm. Next, we have to generate geometries for different values of phi and psi. One can use rotational transformation by Jeffrey and Jeffrey and start from Cartesian coordinates to generate newer Cartesian coordinates. Another way, if you are using internal to Cartesian coordinate conversion method, then it is very easy. One can change continuously from some minimum to some maximum value the torsional angle which we want to change. Conformation map plotting. Starting geometry of a polypeptide is the first step. Then next step is we select rotational angles pairs. finalize initial value, incremental value, and final value for each of these rotational angles. Normally, it is conventional to use rotation from 0 to 360 degrees with the increment of 20 degrees. However, in case of polypeptide backbone, rotation phi and psi is taken from minus 180 to plus 180 degrees, consistent with original definition of these angles by Ramachandran in 1963. Conformation map plotting, generation of Cartesian coordinates, compute potential energies based on the geometry, and create a 2D database for energies. Then find out the lowest energy conformation and lowest conformation energy value. Now find out points or combinations within 1 kcal per mole from the lowest energy and join this by contours. Repeat this procedure for energy interval between 2 to 3 kcal, 3 to 4 kcal, 4 to 5 kcal, and so on, and join boundaries of each region as a contour map. We show in this picture the classical Ramachandran plot. The sterically allowed combinations phi psi are plotted on a two-dimensional Ramachandran phi psi map or plot, alternatively called. The continuous line in that figure shows normal allowed region or full radius in conformational space. The dotted line outside shows extra allowed region if some adjustment for van der Waals allowed distances is done and a reduced radius is used. Also shown in this map are torsional angles phi and psi for different secondary conformations as alpha helix and beta sheet. We show another map again by Ramachandran and Sasisekharan, and in this map they have shown number of different secondary structures commonly occurring in different proteins, like region 1 here is alpha helix, region 2 is left-handed alpha helix, normal alpha helix is a right-handed alpha helix, region 3 is a pi helix, region 4 is a 310 helix, region 5 is 2.2 helix, region 6 polyproline helix, 7 collagen helix, 8 antiparallel beta sheet, 9 parallel beta sheet, and 10 planar pentapeptide ring. What is the importance of Ramachandran plot? The first important thing is the first Ramachandran plot was plotted in 1963, very soon after the first structure of protein, myoglobin, was discovered in 1960. It was great. Second, although Ramachandran used only contact criteria for computation of the sterically allowed regions, and later Sharaga and many people, they used improved empirical potential energy functions. They gave conformation map for Ella, the same which Professor Ramachandran plotted. Ramachandran plot for Ella. Scott and Sharaga in the year 1966 plotted phi-psi map for Ella using the empirical potential energy function described earlier. But the great thing was the general features of this plot were quite similar to original Ramachandran plot, which was plotted using contact criteria only. But the most important thing which came out of this is that even with all improvement of those potential, the general criteria or general features which came out of Ramachandran plot remain unchanged. With the exception of glycine and proline and few residues in the turn region, all the general features of Ramachandran plot are valid for majority of the proteins, and these remain valid for the last 5 decades, and that is the most important outcome of the Ramachandran plot. This has great application for assessing reliability of a protein structure. There are now several computer programs and ready-made softwares which are available for plotting and just transforming the coordinates of proteins into a phi-psi map. These are, for example, ProCheck, MolMol, and there must be several other rather. Actually, there is great interest in this field. The PDB coordinates can be downloaded and one can immediately get a Ramachandran plot using ProCheck or MolMol. Application of Ramachandran plot for assessment of protein structure. Ramachandran plot for DNA clamp protein with both alpha helix and beta sheet structure. PDB ID of the structure was 1SXC is shown in this picture. There are 3 different regions: the red region, brown region, and yellow region, and the phi-psi values are plotted as blue dots in this figure. One can show that red region is the most favored region where majority of the phi-psi values are seen. Brown region is allowed region where still you find number of phi-psi values, and yellow region is not allowed or generously allowed, we can say. This figure is drawn by ProCheck. So, what have we learned today, students? In this today's module, we have seen first the conformational flexibility and rotational angles in a polypeptide chain. Second, we saw what is empirical atom-atom additive potential energy function. We learned how to generate different polypeptide conformations using bond length, bond angle, torsional angle data. We gave mathematical foundation for computation of conformation energy maps. And the most important thing is we elaborated on the Ramachandran plot, its importance, its historical nature, and its great use in protein structure analysis. Thank you very much.